All right, welcome. Calculus is usually taught as this long, boring list of rules you just have to memorize. Well, not today. Today, we're throwing that rulebook right out the window. My goal here is to make you feel like you could have invented calculus. Seriously, all by thinking through one single, simple question.
So let's dive right in with a question you've probably known the answer to since, what, middle school? The area of a circle is pi times its radius squared. But why? I mean, have you ever really stopped and thought about where that formula actually comes from? We're going to treat this familiar fact like a genuine mystery we have to solve.
And here's the cool part. Just by solving this one problem from the ground up, we are going to accidentally stumble upon the fundamental principles of calculus. We're talking integrals, derivatives, and the incredible link that ties them together. And it all starts with a simple circle. Okay, so our first stop on this journey is to unlock this ancient geometric secret. How in the world do you find the area of a circle if you don't have a formula to just plug things into? Let's make this real. Picture a circle. Let's say its radius is 3. We have zero formulas, just our brains. How can we possibly figure out the space it takes up? You can't just measure it with a ruler, right? So we need to get clever. What if we chop it up? Now, just slicing it randomly isn't going to help much. But what if we do it in a way that respects the circle's natural shape, its symmetry? Slicing it into tons of super thin concentric rings, kind of like the layers of an onion, seems like a really promising way to break this big problem down into smaller, manageable pieces.
Now, this is where the magic really starts to happen. We're going to take these circular rings and completely transform them into something that's way easier to deal with, a simple graph.
So here's the game plan, step by step. First, we'll grab any one of those rings, which has some radius we'll just call r. Next, we imagine we can snip it open and unroll it so it becomes a long, thin strip. Then, we'll approximate the area of that strip by treating it like a simple rectangle. And finally, we just need a way to add up the areas of all those different rectangles. Okay, but before we can find the area, we need to talk about how thick our rings are. Let's give that thickness a name, dr. Don't let the letters scare you. Just think of dr as a tiny, tiny difference in the radius as you go from one ring to the next. It's an incredibly small number. So, what's the area of one of these unrolled rings? Well, when you unroll a ring that had a radius r, its new length is just its old circumference, which is 2 times pi times r. And its thickness, like we just said, is dr. So its area is basically length times width, or 2 pi r times dr. Now, it's an approximation, sure, but the thinner we make our rings, the more accurate this gets. All right, so now we have a way to find the area of every single ring in the circle. So what's next? Instead of just adding up a huge list of numbers, let's try to see the problem. Let's take each of our unrolled rectangles and stand them up, side by side, along an axis that goes from 0 all the way to our total radius of 3. And would you look at that? Something amazing happens. Each rectangle's height is its circumference, 2 pi r. So when you line them all up, from the tiniest ring at the center to the biggest one at the edge, their tops trace out a perfect straight line. The equation for that line? It's y equals 2 pi r. And this is the brilliant solution. The total area of all those little rectangles has suddenly become the area of a simple triangle. I mean, how cool is that? Its base is the radius, 3. Its height is 2 pi times the radius, so 6 pi. And we all know the area of a triangle, right? It's 1/2 base times height. So that gives us 1/2 times 3 times 6 pi, which simplifies to pi times 3 squared. Or for any radius r, pi r squared. We solved it. We actually did it. You know, what we just did, this whole process of breaking a problem into infinite tiny pieces and then summing them all up by finding the total area under a graph, it has a name. It's called an integral. We just intuitively discovered one of the 2 huge pillars of calculus. That was beautiful. It really was. But a good mathematician doesn't just solve one problem. They build tools for solving lots of problems. So let's see if our new tool, this whole idea of finding the area under a graph, can help us with something a little harder. So the circle gave us a nice, convenient triangle. But what if the graph is a curve? For example, what's the area under a parabola, like the curve y equals x squared? There's no simple formula from geometry class for a shape like that. Our first method kinda hits a wall here, which means we need another new idea. To crack this nut, we're gonna shift how we're looking at it.
Instead of trying to calculate the entire area all at once, let's zoom in and look at how the area changes when we make one tiny little move. Okay, let's imagine a function. Let's call it a of x, and it represents the total area under that curve from 0 all the way up to some value x. Now for the big question. What happens to that area if we just nudge x forward by a tiny, tiny amount, an amount we'll call dx? Well, that little nudge dx adds a tiny sliver of new area, which we can call dA. And what does that sliver look like? Since it's so incredibly thin, it's pretty much a perfect rectangle. Its width is dx, and its height is just the value of our function at that exact point, which is x squared. So this tiny new chunk of area, dA, is approximately x squared times dx.
Now, this is the clue we were looking for. If you just rearrange that a little bit, you see that the ratio of the change in area, dA, to the change in x, dx, is basically x squared. So dA divided by dx is about equal to the height of our original function. This tells us exactly how fast the area is growing at any given point.
And guess what? This idea also has a name. This ratio, this measurement of how sensitive a function's output is to a tiny little nudge in its input, that's called a derivative. And just like that, we've stumbled our way right into the second major pillar of calculus. So we've got integrals for adding things up, and we've got derivatives for measuring rates of change. What on earth do they have to do with each other? Let's get to the final piece of the puzzle and see how this all clicks together. Think about it like this. On one hand, you have the integral. That's the summing up process. It builds a total area from all these infinite little slices. Then on the other hand, you have the derivative. That's the zooming in process. It tells you the rate of change at one specific point by looking at a tiny, tiny nudge. One builds up, the other breaks down. And here it is, the grand, beautiful, and honestly, kind of mind-blowing connection between them. If you take the derivative of the area function, which is the integral, you get back the original function you started with. Finding an area and finding a rate of change are perfect inverse operations. They undo each other. That is the fundamental theorem of calculus, and we discovered it just by playing with shapes.
So let's end with this thought. We started with something as simple as a circle, and just by breaking it down into its smallest parts, we uncovered a set of tools so powerful it can describe everything from the orbits of planets to the fluctuations of the stock market. It really makes you wonder, doesn't it? What other complex problems out there are just waiting for us to solve them, if only we're willing to look closely at their smallest, simplest parts?